Now, what is the unit of charge? So the unit of charge is always Coulomb. As we learnt, it is simple Coulomb, and how a charge was given. In practical case, electron is the negative charge, what we will consider, and proton is the positive charge. Our entire course is purely depend upon these two charges. As in most of the cases, only the practical case, what we consider is the electron is the charge reference what we are considering. For one electron, what is the charge? Minus 1.6019 into 10 power minus 19 Coulomb. So if we have an electron, then always we need to take this particular charge. And if you have more number of electrons, that's a multiplication of this one we need to consider. So for our convenience purpose only, we will take a little number like 2 Coulomb, 3 Coulomb, 5 Coulomb like that. But in most of the practical cases, the charge will be considered as multiple of this particular quantity. In the same way, a positive charge is called as proton. It's in practical, the proton is called as the absence of electron. Always what we say is, we will take the absence of electron as positive charge. That is the exactly opposite this one, that is minus 1.6019 into 10 power minus 19 Coulomb. So in a neutralizer one, same number of electrons and same number of protons will be there. So whenever it is required, we need to take the charge of an electron as with this particular quantity, as with this particular quantity, and the proton was with this quantity. So whenever it is required, a point charge can be replaced with these two quantities if they are electrons. Remember that one also. So with these basics, that is a point charge, line charge, surface charge and volume charge, we can go for two important laws in our electrostatics. The electrostatics, to understand the entire electrostatics, these two laws are very, very important laws. They are the basic laws, experimental laws, and using these two laws, we can define many quantities which are related to the electrostatics, and we can derive many phenomena. Those two are Coulomb's law and Gauss's law. The first one what we discuss is Coulomb's law and Gauss's law. So these two are the two basic laws what we need to learn in our electrostatics. So they are very much important and useful to solve many problems in our electrostatics. First we will discuss about our Coulomb's law. What is Coulomb's law? So Charles Augustin Coulomb, this is an experimental law which was proposed by Charles Coulomb. What he proposed? He proposed the force between 2 point charges. Let us consider we have 2 point charges Q1 and Q2. So these two are the 2 point charges what we have. The force between these 2 point charges was observed, experimentally calculated by Charles Augustin Coulomb. And what he proposed is the force between these 2 point charges is always directly proportional to the product of the charges what we have, that is Q1 into Q2, and the force is inversely proportional to square of the distance between them. Let us take the square of the distance between them as r square. If the distance between them is r, the square of the distance between them is r square. And the third point, the direction is along the line joining these two charges. So these three are the 3 parameters or 3 points we need to remember related to the Coulomb's law. So once again what he proposed is, the force is directly proportional to the product of these two charges Q1 and Q2, and it is inversely proportional to the square of distance between them, and the direction is along line joining those two charges. That's I am taking a unit vector along the line joining these two charges as a r. So simply this force can be written as, if you want to write down the equation, the force is equals to some proportionality constant, and this force is clearly a vector, some proportionality constant k Q1 Q2 by r square in the direction of line joining these two charges. So here we need to remember two important points, and we need to observe two important points. What is this proportionality constant and what is the direction we are supposed to mention? Since it is a vector quantity, clearly you have to mention in which direction it is. It is like this or like this, and away from the Q2 or away from the Q1, like that we have many directions. By the observation we can say as in which direction it is, right? Before the direction what we do is we will discuss about this proportionality constant. So this proportionality constant was calculated by the Charles Coulomb as 1 by 4 pi epsilon. So before that, what is the unit of our force? The force units are always newtons. So remember that. Now this proportionality constant is 1 by 4 pi epsilon, where epsilon is called as permittivity or dielectric constant of the medium where these two charges were placed. So clearly we need to observe what is the material property there. The permittivity, or it is same, it is called as the dielectric constant of that particular material we need to consider, and we have to substitute here. In most of the cases what we do is we will consider these two charges are in free space. Since these two charges are in free space, we will take that epsilon as epsilon naught, free space permittivity or dielectric constant. So I am writing here epsilon naught. Remember that whenever we are using another type of material, we are supposed to replace this epsilon with epsilon naught. Also whenever we are considering another material, epsilon naught with epsilon. So 1 by 4 pi epsilon naught q1 q2 by r square in the direction of line joining those two charges. This is the equation of our force, Newton. Now what is the unit of this epsilon naught? We are supposed to calculate the units of each and every quantity in the electrostatics and magnetostatics or electromagnetic theory. So if we satisfy the units on the left hand side and right hand side, then the problem is over. So clearly we need to understand what are the units of each and every parameter here. As I said, this is a constant, but every constant will have their units, right? So here epsilon naught units I want. For that, what I do is I will bring this epsilon naught to the left hand side and remaining all quantities to the right hand side. So what I can write is epsilon naught is equals to, what I do, just I will take this one as constant. Here it has no units, right? So charge Coulomb, another charge Coulomb divided by, this force comes to the denominator, that is the Newton comes to the denominator, distance square, meter square. So clearly what you can say is this epsilon naught has Coulomb square per Newton meter square units. So don't think that this is only the unit what we use for epsilon or epsilon naught. We have another unit which is widely used in our entire course, that is farad per meter. That we will discuss later, how this farad per meter came. But till now, just you remember this epsilon has units Coulomb square per Newton meter square. Now with this substitution, simply what we can say is F bar is equals to 1 by 4 pi epsilon naught q1 q2 by r square in the direction of line joining these two charges. Now we are going to discuss about this direction also. We discussed about the constant what we have. Now we are going to discuss about the unit vector in that particular direction. So to observe that unit vector, so what we have to observe? Clearly remember one point, that we need to observe the force where we are calculating. So where, so the word where is very very important here, where we are calculating the force. So why we are calculating, when we are calculating, it's a don't bother about all those things. Where we are calculating the force is very important. Observe, we are taking two charges here. We are calculating the force between those two charges, absolutely right. But where? The force is calculated at Q2, or the force may be calculated at, here, where? It's at Q1, or the force which is calculated somewhere when the charge is here. Like that, you need to observe where the force will be calculated. If the force is calculated at Q2 because of Q1, the force calculated at Q2 because of Q1, I will denote that force as F12. The force calculated at 2 because of the charge 1. Blindly remember, from first to 2, the force is flowing from 1 to 2. The force is in this direction. The force acting on 2 because of charge 1. That is the one type of force you can observe. And next force what we can observe is the force acting on 1 because of 2. That is, blindly remember once again, the force is acting from 2 to 1. Right? So this is the direction of our force. So purely depend upon the force where we are calculating, the direction will be decided. We are not supposed to take the direction as our wish. So we are supposed to take the direction purely depend upon where we are calculating. If you are calculating the force at 2, take this direction. If we are calculating force at 1, that is the force acting from 2 to 1 we are supposed to take. Now how to represent the direction in terms of their unit vectors, how to obtain the unit vector and how to replace this AR with that equivalent. Now we will observe what are these two forces and how to obtain the equations for these two forces. Let us consider first F21, that is the force from 2 to 1, the first one to the second one. That's, remember always the first suffix to the second suffix. F21 is equals to, as we said, the proportionality constant is same, 1 by 4 pi epsilon naught, I am considering this one for free space. The charge 2 q2 multiplied with charge 1 q1 divided by, now what I want is the distance. The distance is always r, so nothing more than that. But for our convenience, what I do is the distance from 2 to 1, I will write that one as r21 square, and the unit vector from 2 to 1, that I will represent r21 like this, and the unit vector in this direction is r21. That is the force from 2 to 1, the distance from 2 to 1, the unit vector is also from 2 to 1. So everything I substituted here, 1 by 4 pi epsilon naught q2 q1 by r21 square a r21. Now we need to substitute this a r21, that is the unit vector from this point to this point. Always the unit vector can be calculated using its vector, distance vector. Take the distance vector and divide the distance vector with its magnitude. So what is a r21? The a r21 can be obtained simply r1 minus r2 divided by magnitude of r1 minus r2. It is magnitude, right? Now remember, don't go for any position vector etc etc. Just for obtaining any distance vector between 2 points, subtract the first point from second point. Here what we require is the distance vector between 2 and 1, right? 2 1 we require, so subtract 2 from 1, that is r1 minus r2 divided with its magnitude. So the distance can be simply obtained with this equation, and the total unit vector can be obtained with r1 minus r2 divided by r1 minus r2, that is its magnitude. So replace here, which is equals to 1 by 4 pi epsilon naught q1 q2 divided by, instead of r21 I am writing magnitude of r1 minus r2 whole square. Instead of a r21 I will write r1 minus r2 divided by magnitude of r1 minus r2. Clearly observe here, this r1 minus r2 is the distance vector between 2 and 1, that is from 2 to 1, and this magnitude of r1 minus r2 is the scalar quantity. This is the vector quantity, this is the scalar quantity. If you make it a simple term, what we get is 1 by 4 pi epsilon naught q1 q2 by this is the equation what we can get for F21, that is always the force from 2 to 1. So clearly observe this one, this r1 minus r2, once again I am saying this r1 minus r2 is the distance vector, and this r1 minus r2 is the magnitude of that particular vector. Now in the same way, what I do is I will try to define F12 also, force acting on 1, so because of force acting on 2 because of 1, that is directly F12, the force acting on 2 because of 1, the force from 1 to 2. Once again write down the equation for this one. The constant is 1 by 4 pi epsilon naught, the charges are q1 q2 divided by, now here also we require the distance between these two. For our convenience I will take the distance as r12, that is the distance is always a scalar quantity, remember that, r12 multiplied with its unit vector a r12. Now once again we need to replace this a r12 with its equivalent. So how to obtain that a r12? As I said, a very simple one, don't go for position vectors or etc. Just subtract the first one from second one, that is r2 minus r1 divided with its magnitude. Here it is magnitude. Now replace here, then what it becomes, 1 by 4 pi epsilon naught q1 q2 by, instead of this r12 square, this is r12 square, instead of this r12 square I can write magnitude of r2 minus r1 square multiplied with its unit vector, that is r2 minus r1 divided by magnitude of r2 minus r1, that is its magnitude. So once again clearly observe, this is the distance vector and this is the magnitude of this distance vector. So this is a vector quantity, and in the denominator what we have is a scalar quantity. Now if you simplify this one, what we get? Just 1 by 4 pi epsilon naught q1 Q2 divided by magnitude of R2 minus R1 whole cube multiplied with R2 minus R1. Just observe the two forces what we derived. F21 is this quantity what we have, and F12 is this is the quantity what we have. If you closely observe these two quantities, the magnitude what we are considering is same, 1 by 4 pi epsilon naught Q1 Q2 by R2 minus R1, that is R cube. Here also it is 1 by 4 pi epsilon naught Q1 Q2 by R cube. So the magnitude is same, but if you observe the vectors, they are opposite in direction. Since the vectors are opposite in direction, clearly you can say that these two forces what we are calculating are same in magnitude but opposite in direction. So what you can write is F12 is equals to minus F21 always. So whenever we are calculating the force between 2 point charges, if you want only magnitude, don't bother about the direction, then just calculate the magnitude. So from 2 to 1 or 1 to 2, whatever it may be, the magnitude is same. If you want the direction, then specifically you need to identify where you are calculating the force. So for clearly observe, so whenever you are observing the direction, then observe where you are calculating that particular force, and according to that we need to consider the direction, right? So that direction will be substituted, and if you observe, this F12 is equals to minus F21. Now instead of only 2 point charges, if we have more number of point charges, how to obtain the force between them? Simply remember the superposition principle is applicable here. Whenever we have more number of point charges, we are calculating the force acting on a single charge because of all the charges what we have placed surrounding that one. Then the force is summation of the individual forces. That is simply the principle of superposition. That what we will write down in brief here. Now let us consider we have a point charge Q0 here, and on this point charge, because of Q1, Q2, Q3 up to some Qn, we need to calculate the force. So because of all these charges, what will be the force which can be acts on this point charge Q0? A simple technique that calculate the individual forces, that force from 1 to 0, that is the force will be in this like this, and the force from 2 to 0, the force from 3 to 0, like that the force from n to 0. Now the total force acting on this particular charge Q0 is simply the summation of all these forces. That what we can write is the total force acting on this Q0 is equals to F10 plus F20 plus F30 and so on plus Fn0. So what we need to do is we need to take the individual forces and calculate them and add them. What we will get is the superposition of the force, that's simply the total force acting on our charge Q0. Now if you write down the equations of these forces, 1 by 4 pi epsilon naught is constant for all. That's why I am taking this one as constant common to them. So 1 by 4 pi epsilon naught into Q1 Q0 divided by this distance vector is R0 minus R1 whole cube multiplied with the vector R0 minus R1. So R0 minus R1, this is the distance vector and this is the magnitude of the distance vector. And the second force plus Q2 Q0 divided by, and what is the magnitude here? R0 minus R2 whole cube, and for this one the distance vector is R0 minus R2 plus, for the third one, so you can write the same quantity. What I am writing is the n term, that is Fn0, that is Qn Q0 divided by magnitude of, just you write down the magnitude for this particular force, that is R0 minus Rn whole cube multiplied with its distance vector R0 minus Rn. So just you observe what we are doing here. We are calculating the individual forces and we are adding them. So if you write down the general equation, the general equation will be like this, which is equals to 1 by 4 pi epsilon naught, that here I am taking a constant k, to write down this one, and before that this q naught is common in everywhere. So that's why I'll take this q naught also as common quantity. So q naught divided by 4 pi epsilon naught is the term which is common to all. Sigma k equals to 1 to n elements are there. Qk divided by, here the magnitude of all these vectors, that is r naught minus rk whole cube multiplied with its distance vector, that is r naught minus rk. So this is the equation what we have for the entire force which is acting on our charge 0 q naught. So this is called a simple superposition of the force which are acting on a single charge. Now we will have a simple example how a particular force acting on a charge. So with this example we can understand easily how a charge will be calculated and how to observe a charge. So don't go for the calculation, just we will observe how it is acting. Now a problem is given like this. 4 charges were placed on the 4 corners of a square, and this square was symmetrically placed on YZ plane. Remember that the 4 charges were placed on the 4 corners of a square and this square was placed symmetrically on YZ plane. Now what will be the total force acting at the center point of the charge or the center point of the square? So let us take the charge which is located at the center point of the square. So this is the charge which is located at the center point of the square, as the problem defined like this, that is symmetrically placed that this square is symmetrically placed on YZ plane. Since it is symmetrically placed on YZ plane, definitely you can say that the center point is at origin, right? We are placing a charge at origin and we are going to calculate the total force acting because of these 4 equal charges. If the 4 equal charges are placed at the 4 corners of a square, we are going to calculate what is the total force acting on the center point of that square. For that, let us take these 4 charges as q1. Since they are same, I am taking them as q1, 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 and let us take this as q naught. The charge which is placed at the center point is q naught. Now, how to obtain the total force which is acting on this particular charge q naught? So, as per our superposition, take the force in this particular direction, that is the charge force acting on charge q naught because of this charge q1, and the force acting on the same q naught because of this charge q1, the force acting on the q naught because of this charge q1, and the force acting on this q naught because of this charge q1. So let us take them as F1, F2, F3, F4. So just identify that the force between these two is F1, F2, F3 and F4. Now we are going to calculate the force acting on this q naught because of these 4, right? The force acting on q naught is F is equals to the summation of these 4 forces, F1, F2, F3 plus F4. But before going to the calculation and substitution of different parameters which are obtained from this figure in the formula, just you observe them. These 4 charges are same and the square was symmetrically placed on YZ plane. Since it is symmetrically placed on YZ plane, from the center point this distance is equals to this distance, and which is equals to this distance and this distance. So from the center charge the distances for q1, 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 q1. So these 4 locations is same, and as we discussed, the force from 1 to 0 and force from this one to 0, force from this one to 0, force from this one to 0 will be in the same directions as we mentioned in the figure. Now observe them. If you observe this force, that is F4 is exactly opposite to F2 and the magnitude is also same. Since the charges quantities are same, the magnitude is same and the direction is opposite to this one. In the same way, F1 and F3, they are same in magnitude but the direction is opposite. So clearly what you can say is F4 is equals to minus F2, F1 is equals to minus F3. So if you substitute them, what we get is 0. So the net force acting on the center charge, what we are considering, because of 4 equal charges on this one, they are placed on corners of a square, is 0. If you remove any one of these charges, then obviously some force will act on that one. That is also only because of this charge. Let us take this force, this charge was removed. If this charge was removed, you have 3 more forces, that is F1, F2 and F3. But in that one also F1 and F3 are opposite in direction and same in magnitude. So these two will be cancelled, that the net force acting on is only because of this charge. So the same case is applicable for another one also. 8 equal amount of charges were placed along the corners of a cube. And what will be the total force acting exactly at the center point when there is a charge? Then simply what you can say is the 0. The force acting on that particular one is 0. Right, like this, what you can say is we can calculate the individual forces and you can add them. That is practically, if you want to calculate it, we have to take the equation and substitute it. But with the observation also, we can say what is the particular force acting on a charge. Now, we are going to define another term is in terms of this force. Already we learnt what is force between them. Before that, just let me explain what are different forces we have. Since we are considering 2-point charges, they may experience attractive force or repulsive force. When they will experience attractive force, when they will experience repulsive force. If the quantity of these two is, if they have same polarity, let us take this is some plus q1 and this is some plus q2, that these two charges what we are considering have same polarity. If they have same polarity, obviously the force is the repulsive force. So whenever we are calculating the force at charge 1, because of charge 2, it is a repulsive force, that this is your F21 direction. The force because of the charge 2 on Q1 is the repulsive force on Q1. In the same way, the force because of charge 1 on Q2 is F12, that is also the repulsive force. What it does is just it repels the charge, opposite charge, when the polarity is same. In the same way, if we are considering two opposite charges, let us take this is minus q and this is plus q. So if we have two different charges, let us take q1 and q2, two different charges with opposite polarity, then there will be force of attraction between them. So these two forces will be attracts towards. That is, whenever the force is calculated at charge q2 because of q1, then that is attractive force. That is, it attracts the charge q2 towards it. That is simply this is F12. The force acting on 2 because of 1 is attractive force. In the same way, here it is F21. The force acting on 1 because of 2 is attractive force. So clearly we need to observe which type of force it is, whether it is attractive force or repulsive force. That is purely depend upon the polarity of the charges. Right? With this introduction of the force, we can go for another quantity. It's a very important quantity in our electrostatics called as electric field intensity. How that electric field intensity was defined. Before that, just you imagine one scenario. Here we have two charges. How the electric field intensity was defined. So let us consider a scenario. Here we have two charges. Let us take this is charge 1 q1, charge 2 q2. What we are doing is just we are calculating the force between these two, or the force acting on one because of another. Let us take the force acting on q2 because of 1, that it will be described as F12. Here we are calculating the force, remember that. Obviously the force is directly proportional to the product of these two charges and inversely proportional to the square of distance between them, as the entire thing is same. So here what we are doing is we are calculating the force. Now we are dividing this force with this charge, that is we are calculating the force per charge, that is F12 divided by q2 I want. Now what is the equation for this F12 by q2? Here clearly observe what we are calculating. We are calculating another quantity. That quantity is calculated as force per charge. The force which is observed at this particular charge per that particular charge. Now how you can write this F12? So the equation for F12 is q1 q2 by 4 pi epsilon naught r12 square a r12. That what we can write. Now what I am calculating is this force per charge, that is F12 divided by q2, the force which is calculated here per charge, which is simply Q1 by 4 pi epsilon naught R12 square A R12. Now observe this result. This is the result what we got. Now if you observe the result, in that result this particular quantity what we have calculated just now is purely dependent upon Q1 only. It's not depending on the Q2 what we have. So it's purely dependent upon Q1 only. And same as in our previous one, it's inversely proportional to the square of distance between them. The direction is also same, right? Now you can define this one as the field quantity. That field quantity is the force field quantity, the force per charge. That force field is also called as electric field intensity, denoted with symbol E. That capital E is the electric field intensity what we have. That electric field intensity is also called as, once again, force field, force per given charge, which is purely dependent upon the charge what we have. It's initially, that is Q1, and inversely proportional to the square of distance between the charge and the point of observation. Now here what we are doing is we are taking this one as point of observation. Don't think that this is the location of another charge. Here we are not considering about this charge. Don't bother about this charge. Now this charge was removed completely. We are calculating another term called as electric field intensity at this particular location. So here clearly this R12 is now the distance between the charge and point of observation. Now this is called as electric field intensity. Now what are the units of this electric field intensity? As I said, we require the units of this electric field intensity. Force per charge. What is force per charge? Newton per Coulomb. So the units of our electric field intensity are Newton per Coulomb. But widely what we use is volt per meter. We will come across this volt per meter later when we discuss our potential. So in terms of potential it is volt per meter, and if you want to describe the same quantity in terms of its force and charge, just it is Newton per Coulomb. But the widely used one is volt per meter. So both are same. Remember that. Now once again clearly remember, this electric field intensity is a quantity which can be observed at a particular point, and it is defined as the force per charge at that particular point. Now can you find any similarities between the force and electric field intensity? So the force and electric field intensity both are inversely proportional to the square of distance between them. And if you observe this electric field intensity, it has no particular direction. It's purely dependent upon the point of observation. Same as our force. The force is purely dependent upon where you are calculating the force. The electric field intensity is also purely dependent upon the point of observation where you are calculating the electric field intensity. Let us take this is the charge what we have, and this is the point where we are calculating our electric field intensity. Then the direction is always like this. That is a line joining the charge for point of observation. Or if you are calculating the electric field intensity here, once again the direction is always from charge to point of observation. So here a generalized observation can be like this. For a fixed distance, the magnitude of the electric field intensity is same. The direction may vary, but here clearly the magnitude of our electric field intensity is same at a fixed distance everywhere in the space. That's what we need to remember. Now what is the equation of our electric field intensity? The electric field intensity equation is written as Q by, a generalized equation. I am not taking Q1 or Q2, just we have only one charge. Because of that charge, the electric field intensity can be observed in space, right? So that charge I am considering Q by 4 pi epsilon naught. Here the medium what I am considering is free space again. That's why I will take this one as epsilon naught r square a r, where r is the distance between the charge and the point of observation. A r is the unit vector in that particular direction. Now if you have more number of charges, let us take at this point we want electric field intensity. Now this electric field intensity is because of more number of charges, Q1, Q2, Q3 and so on, Qn. So we have more number of charges. Because of all these charges, if you want to calculate the electric field intensity at this particular location, same as our force here also, the superposition is applicable. What we need to do is we need to take the electric field intensity because of charge 1, E1, the electric field intensity because of charge 2, E2, because of charge 3, E3 up to En. Add them, then that will be the total electric field intensity at this particular point. That is E is equals to E1 plus E2 plus E3 plus E4 and so on plus En. So here what we can say is, to calculate the electric field intensity or to observe the electric field intensity at any location, what we require is a charge. If there is no charge, obviously the electric field intensity is also equals to 0. So in absence of charge, we couldn't find any electric field intensity. If the charge is there, whatever it may be the type of that charge, for an example and for the analysis purpose till now, we are using a point charge. But if you have a line charge, definitely some electric field intensity will exist. If you have a surface charge, electric field intensity will exist. If you have a volume charge, the electric field intensity will exist. If there is no charge, no electric field intensity will exist. We need to remember that point. So in absence of charge, no electric field intensity will be there. So the electric field intensity always will be distributed around the charge where we are considering, around that particular charge in the space, that may be space or some other dielectric medium. Now how this electric field intensity will be observed for positive charge and negative charge. Now observe the equation. If you observe the equation, E is equals to plus Q. If it is positive charge, always we can say that it is away from the charge, radially outwards, that's what we can say. If it is negative charge, radially inwards, that is towards the point charge what we are considering. So in general what we can say is, whenever there is a positive charge, let us take this is a positive charge, the electric field intensity is always radially outwards. That we can say that a positive charge is a source of electric field, it is a source. And whenever there is a negative charge, then the electric field intensity is radially towards the charge. That what we can say is, it is sink of the electric field. So the electric field will be generated at positive charge and that will be ends at negative charge. Now in some case, if you have same amount of positive and negative charges, let us take this is plus Q and this is minus Q. The charge is same but they are opposite in polarity. Then what we can expect is, the electric field intensity will always flows like this. That the electric field intensity will generates at this positive charge and ends at our negative charge. That what we can expect in an equilibrium state, right? So clearly remember, always the positive charge is the source and a negative charge is always a sink. So the lines what we have drawn to understand this electric field are called as electric field lines. Simply they are field lines. So the electric field lines are the lines which are drawn to understand our electric field intensity. So wherever we are considering at this particular location, this is the direction of our electric field intensity. If you are considering at this location, this is the direction of our electric field intensity, that we need to consider the tangential direction at every location on that field lines. So just remember that these field lines are the imaginary lines what we are drawing to understand how the electric field intensity is distributed in space or the medium what we are considering. So whenever there is a charge, these field lines will exist. So this is a simple quantity what we have defined as electric field intensity. This electric field intensity may be because of the point charge. In this case we discussed about only point charge. If we are considering line charge, how to write down this electric field intensity? Very simple, that take this Q in terms of line charge density. So if you are considering that Q in terms of line charge density, then the electric field intensity is for line charge what we are considering. How to take it? How to write down the equation for this electric field intensity in case of line charge? As I said, just replace this Q with its equivalent in terms of line charge density. Line integral of rho L dl by 4 pi epsilon naught r square a r. Here what we need to do is, we need to consider the projection from line to the point, where r is the distance which is drawn, a normal drawn from line to the point, and r is in the same direction of r. This is in the case of our line charge. If you are considering surface charge, then the same equation can be written as surface integral of rho s ds by 4 pi epsilon naught r square a r. Here this rho s ds with surface integral will give us the total charge, and this ar and r, this ar is the unit vector which is in the direction of r, and r is the normal which is drawn from a surface to the point. So always take the direction from surface to the point. Here in this case it is line to the charge at the point what we have, and here it is surface to the point. And in case of volume, just it is the volume integral of rho v dv by 4 pi epsilon naught r square a r. That this volume integral of rho v dv gives us the total charge, and this r is the distance between the volume and point where we are observing. Just this is the simple procedure for obtaining the electric field intensity in case of their respective charges. If it is line charge, this one, surface charge, this one, volume charge, this one we are supposed to use. Now we will define one more quantity. So which is independent of space. Why we require another quantity which is independent of space? Just to observe force and electric field intensity, what we discussed till now. What is the equation of force? F is equals to some constant k. This constant is purely depend upon our space, right? How it is defined? 1 by 4 pi epsilon naught when it is free space, or 1 by 4 pi epsilon when it is any medium, dielectric medium. Q1 Q2 by r square in the direction of r, right? Now in the same way, what is the equation of electric field intensity? E is equals to same equation, that is 1 by 4 pi epsilon naught for free space, q by r square a r. If we observe these two equations, we have a parameter called as permittivity or dielectric constant of the medium, right? Now if you want to calculate this force, definitely the parameter epsilon must be known to us, which is related to the material what we are considering. If you want to calculate the electric field intensity, definitely we must know what is epsilon, that is the dielectric constant of the material, and we must know what is this epsilon value for that particular material. So here clearly the calculation of force and electric field intensity, these two are purely depend upon our material. Now I want another quantity which is independent of the material, that is which is independent of the material characteristics, that what I can say. Now for that another quantity was defined like this: d is equals to epsilon e. So d equals to epsilon e. What is this d is equals to epsilon e? If you take this epsilon e or epsilon naught e for free space, then what we will get here? 1 by 4 pi q by r square a r. Now here this is also a vector. This d is not a simple scalar. This is also a vector, but it was given as 1 by 4 pi q by r square a r. So if you are calculating this particular quantity, clearly this is independent of the medium property what we are considering. Just what it requires is a single charge and the distance between point of observation and this charge. So irrespective of the material you can calculate this one. That's why it is said to be a quantity which is independent of the medium, and whatever it may be the medium, you can calculate this one. After that one, if you know the medium property, or we can calculate our electric field intensity, or if you know the medium, or we can calculate force. So if there is no medium property is available, then clearly this is the most suitable quantity what we have. What is this and how it is defined? So this is simply defined as epsilon naught into E, and what it is called. Before that, just you examine the dimensions of this one or the units of this one. Q, Coulomb per distance square meter square. Something we are calculating per meter square. Meter square means area, right? We are calculating a quantity per given area. That's why it is called as density. What is this density? This density is displacement. What we are calculating, the displacement is the electric field intensity. That displacement density as simply per area. This is also called as flux density. Whenever this quantity is calculated, you can observe, so something is flowing through that particular surface. That quantity is this C per given area. Now this C is not charge. Don't think that it is charge. It is flux. The flux which is passing through that particular surface is called as surface charge density, or in other words it is called as flux density. That flux density is simply D. So what are the units of that flux density? Coulomb per meter square. So whenever you have a surface and if the flux is flowing through that surface, if you want to observe that one, this flux density is most useful. Here we are not calculating or we are not using any material property here. So don't take the material property, just calculate this particular quantity. So we are using this 1 by 4 pi q by r square AR. That's enough. After that one, later if it is required, you can calculate E from this D, or later if required, you can calculate force from this T. So remember that point. This D is a pure independent quantity with respect to the material what we have, right? Now from this D we can take flux. As we said, this is the flux density, electric flux density or the displacement density. From the density you can calculate the original quantity, that is called as flux. So how that flux can be calculated? By multiplying this density with its area. So simply multiply D with its surface area. Yes. So if you can multiply this flux density with its area, what we will get is the total flux which is passing through that particular surface. Now in terms of the differential surface, we can write this equation as integral d ds. Differential surface is the differential surface what we are considering through which the flux density is observed. Here this integration is purely surface integral. Now what are the units of this psi? So clearly the Coulomb per meter square are the units of our D, and it is multiplied with its area meter square. So simply the flux units are Coulomb. Even though the units are Coulomb, don't think that it is equals to the charge. It is a quantity which can be calculated which is passing through the surface. Just it is a scalar quantity which is passing through that particular surface or crossing the surface. But D is a vector quantity that can be observed at a particular location on a surface, right? E is the vector quantity, F is the vector quantity. Now what we do is just we will compare these four parameters for a quick reference. So how they are and how to observe the units, etc. So let us consider the comparison between all these quantities. Force what we have, electric field intensity is defined, electric flux density is defined, the psi we can calculate from electric flux density. Now one by one we will observe this force is a vector quantity. Electric field intensity, this is also a vector quantity. D, this is also a vector quantity. Psi, this is not a vector, this is a scalar quantity. That something is how much particular quantity is passing through it. That's why it is a scalar quantity. Next, it is directly proportional to two charges magnitudes, that is proportional to Q1 and Q2. Here this electric field intensity is directly proportional to only the charge what we have. So because of this charge, this will be calculated at some free location, right? So D is also directly proportional to charge what we have, and this scalar later we will discuss about how it will be related to the charge after discussion of the Gauss's law, right? Next, it is inversely proportional to square of the distance between these two charges. This is also inversely proportional to square of the distance between point of observation and location of the charge. This D is also inversely proportional to square of the distance between point of observation and location of the charge. Leave this one, we will discuss about this one later. Next, what is the direction of this force? Line joining the two charges. So since we have two charges, the line joining these two charges gives us the distance. Here what is the direction of our electric field intensity? Purely it is in the direction of our point of observation and charge, that is from charge to the point of observation. We can write this one also A R. D and E always will be in the same direction. So whenever E is in this direction, D also will be in the same direction. So if the E is in this direction, D also will be in the same direction. So here D also will be in the same direction. Since it is a scalar, it will not have any direction. Now clearly, which one is independent of the medium and which one is depending on the medium? Force, clearly it is depending on the medium. What we have is epsilon naught or epsilon in this equation. Since we have epsilon in this equation, it is medium dependent. Now go to the E. E also is medium dependent. In E also what we have is epsilon. That's why it is medium dependent. Now come to the D. D is purely independent of the medium. We have no epsilon here. So it is medium independent. And psi is also medium independent. So this is a simple comparison that the force, electric flux density D, these three are vectors, this one is a scalar, and they will vary differently with respect to the charge what we have. And if you are taking the medium property, these two are depending on the medium and these two are independent of the medium. So in one of the questions, a question was given like this: among the following quantities which are independent of the medium, the options were given like this. Option A, E psi option B, D E option C, D psi option D, E F. So the question is simply, which among the following is independent of the medium? Just observe, this D and psi are independent of the medium. So the option C what we need to choose, and clearly we need to observe the purely depend upon their individual formulae. This is a simple comparison of all the parameters what we learned till now. These are the basic parameters what we have to remember. And so one more parameter what we have is the potential. Later we will discuss about that potential. Before that we will relate all these parameters in different ways, and we will calculate the electric field intensity for different charge densities. Right? Till now we discussed about the Coulomb's law. We need to learn one more law that is called as Gauss's law. So using that Gauss's law, we can get the electric field intensity in easiest way. It's a very easy way we can obtain the electric field intensity for any type of charge. That it's a very useful law in our electrostatics. We will discuss now. Another important law what we have in our electrostatics is the Gauss's law. So this is called as another form of our Coulomb's law. This is also useful for obtaining the electric field, but this is very useful law and very interesting, easiest law. So if we observe what is this Gauss law and how to apply this Gauss law, then it is very easy to recollect or define electric field intensity for any type of charges. So what we do is we will discuss what is this Gauss law. Later we will apply this Gauss law on different types of charges. So how this Gauss law was defined? Let us consider a closed surface. So here I am considering a closed surface, that a closed surface always will forms a volume. Right? Now the total flux leaving through this surface, the total flux which is leaving through this surface of this closed one is always equals to the charge enclosed. That what we are doing is we are calculating the total flux which is leaving through this one. As we discussed, this flux is defined with psi, as denoted with psi. We are calculating the total flux which is leaving through the surface of that particular volume. That volume was formed by the closed surface. That flux is equals to the total charge enclosed within this particular volume. That is a very simple Gauss law. So in the notation, how to write down that one? The total flux leaving, write down this one like this. The total flux leaving through the surface of the closed volume, that's a volume what we have, which is equals to the total charge enclosed. Here clearly remember, so whenever we are observing this Gauss law, closed surface is very important. We require closed surface. We are calculating the flux leaving through that surface and charge enclosed within that closed surface. These two are important. So if you take them, then they are equal as per our Gauss law. Now if you take the total flux leaving through that surface, how to calculate the total flux leaving through that surface? For that, calculate or take the differential surface on that particular volume what we have. Consider that one as ds and observe what is the flux density which is flowing through that particular differential surface, that is d. Now if you integrate this d for the entire surface, then we will get the total flux leaving through that particular surface. So this can be calculated using closed surface what we have, integral d ds. So for the closed surface, if you integrate this d with respect to the ds, what we get is the total flux leaving. Now how the total charge enclosed within this one can be calculated? Since we are considering a volume, the closed surface will form a volume, we need to consider the volume charge density here. Let us take the volume charge density of the closed surface is rho v. So if you integrate that volume charge for the entire volume, what we will get is the total charge within this particular volume. So this charge enclosed can be calculated using volume charge density rho v. So once again clearly observe here, the total flux leaving can be calculated using the flux density d. Total charge enclosed can be calculated using volume charge density what we have, since it is a closed surface. Now we have a very good theorem, that is a divergence theorem, which can relate always a closed surface with volume. So here we need to apply the divergence theorem. So apply the divergence theorem. If you apply the divergence theorem here, what we will get? Say closed surface can be converted as a volume integral. Just you write down this one as a volume integral. A volume integral of this one is del dot d, divergence of d, ds is equals to, here it is a volume integral of rho v dv. Just what I did is I applied the divergence theorem here. As I am applying the divergence theorem, the closed surface can be converted as volume integral. Now bring this right hand side term to the left hand side. Then what we get is the volume integral of del dot d minus rho v ds is equals to 0. So if you bring this right hand side term to the left hand side, volume integral of this del dot d minus rho v dot ds is equals to 0. Now observe this integration. Then for any arbitrary surface what we are considering, clearly the term equals to 0. So if you are considering an arbitrary surface ds, then obviously the integrand del dot d minus rho v is equals to 0. So if you take this del dot d minus rho v is equals to 0, right, here the integrand del dot d minus rho v is equals to 0. So if you write that one, del dot d is equals to rho v, that what we get. This particular equation is very useful equation in our electrostatics, that this will be useful for calculation of many parameters. The del dot d is equals to rho v is called as the Gauss law equation, and in other words it is also called as Maxwell's first equation. We will come across those Maxwell's first equation, second equation later, but for time being remember that this del dot d is equals to rho v is a very important equation which gives us many parameters in our electrostatics. Now this is point form. This is in point form or differential form. Since it is a differential operator, this is in differential form. So previous to that we wrote one more equation, that is the closed surface integral of dds is equals to volume integral of rho v dv. This is in integral form. So what we can say is this is a Maxwell's equation in point form. This is a Maxwell's equation in its integral form. So we will discuss about those Maxwell's equations later. Before that, what we do is we will discuss in detail about this particular equation del dot d is equals to rho v. How this will be modified and where this can be applied, how this will be applied for different situations. Before that, just examine what are the units of these two. So if the units are satisfied, then obviously this equation is right. This del dot d, del operator, if you consider that in rectangular coordinate system, it is dou by dou x. Let us I will consider this one as d, dou by dou y plus dou by dou y d plus dou by dou z d. That what we will have. That dou by dou x, this is 1 by distance, 1 by meter. And what is d? D is Coulomb per meter square. So the units are Coulomb per meter cube. On the left hand side, the units are Coulomb per meter cube. On the right hand side, what we have is rho v. What are the units of rho v? Volume charge density, Coulomb per meter cube. So the units of our left hand side and right hand side, so both are same. So the equation what we derived is right. So don't think that so del dot d is equals to rho s, del dot d is equals to rho, del dot d is equals to rho l. So they are not correct. Del dot d is equals to rho v is only the correct. So whenever it is asked in the examination that calculate the charge density when our flux density is given, don't try to calculate the surface charge density or line charge density using this equation. Right? So this equation is useful for calculating volume charge density only. Now how this equation can be interpreted? Del dot d is equals to rho v. That del dot epsilon e is equals to rho v, that what we can write, since d and e are related with epsilon e. If it is applied for a charge free region, since it is charge free region, there will be no volume charge density. The same equation can be written as, for a charge free region, the same equation can be written as del dot epsilon e is equals to 0. That here, if this particular medium what we are considering, even though it is charge free, if the particular medium is homogeneous medium, homogeneous means everywhere this epsilon is fixed, that this can be treated as constant, it is uniform. We can write this one as del dot e is equals to 0. For a charge free homogeneous medium, this can be written as del dot e is equals to 0. So this case is very much useful in our wave propagation. So whenever we are considering a wave in free space, this free space will be treated as a homogeneous medium and it is charge free region. That's why we will take this rho v as 0 and this epsilon also will be removed. That del dot e is equals to 0 is the equation which is required for us. Now a homogeneous charged region, that is some charge is there but it is homogeneous. Then how this equation can be written? Del dot e is equals to rho v by epsilon. Since it is a homogeneous medium, this epsilon can be brought out from the del operator, and this rho is already there, some charge is there, right? Like this, we need to interpret all these equations. So whenever it is required, we have to modify that particular equation. So del dot D is equals to rho v is a very much a basic equation which is useful for understanding the wave propagation also. So this is a very important equation we need to remember.